This chapter 4 describes the measurement of VaR by means of the historical simulation approach, followed by the Monte Carlo simulation approach. We begin by recalling a critical assumption of the variance-covariance approach, namely that percentage changes in risk factors are normally distributed around their mean. Numerous studies have concluded that the actual distributions of returns for many asset classes are not, in reality, normally distributed, but rather have fat tails, meaning that extreme changes in prices or levels occur more frequently than is assumed under the normal distribution. This results in an underestimation of the true probability and magnitude of extreme losses where a normal distribution is assumed. The graph appearing now depicts in dark red the actual distribution of percentage changes in a specific unspecified risk factor and contrasts it to that under a normal distribution, shown in blue, assuming the same volatility in both cases. We have indicated in various colors the areas within plus or minus 1 sigma, plus or minus 1.65 sigma, and plus or minus 2.33 sigma to facilitate your comparison of these distributions. Two important observations are noted. First, as mentioned earlier, extreme events have a higher probability of occurrence under the actual distribution. And second, unlike here, the actual distribution is usually non-symmetrical, with the probability of extreme adverse outcomes being higher than that of extreme favorable ones. For these reasons, many financial institutions resort to an alternative approach for the calculation of VaR, known as the historical simulation approach, which enables them to reflect more accurately the characteristics of the distribution just mentioned. This approach is simple to apply and requires no calculations of volatility or correlation. Its main weakness lies in its flawed assumption that historical events and data are reasonable predictors of future ones. We will demonstrate shortly how much the VaR calculation under this approach depends on the precise choice of historical sample. The present approach begins as before with the determination of the position's sensitivity to unit shifts in risk factors, both linear sensitivities and convexity adjustments, i.e., steps 1 and 2 in our 5-step process. And then it requires us to proceed as follows. First, we calculate the percentage changes in risk factors over the chosen historical sample. Second, using the position's linear sensitivity to shifts in risk factors as well as the convexity adjustment, we calculate the changes in position value relative to inputs from bullet point 1. Third, we rank the outcomes from paragraph 2 from worst to best. And fourth, we set VaR quite simply to equal the outcome whose ranking under bullet point 3 above corresponds to the targeted confidence level and based on the total number of observations in the sample. For example, if we use 500 observations, the 99% VaR is set equal to the 495th worst outcome, 500 times 99%, and would mean that only 5 observations are worse than the result calculated. A shortcut for steps 3 and 4 is available via the percentile function in Excel, which returns the kth percentile of values within a sample of data. For example, the 99% var will simply equal the first percentile, since the percentile function measures from the smallest observation up to the largest. Be careful here not to input 0.99 instead of 0.01 in the Excel formula. We next illustrate this historical approach by revisiting again some of our earlier examples. For our first illustration, we calculate on this worksheet Histo var foreign equity, the 99% daily var for the foreign equity position, consisting of 100,000 Vivendi shares, whose risk factors, we remind you, are the spot price of Vivendi stock and euro-dollar spot. We will use a sample that includes the 500 most recent daily closing prices for Vivendi stock and for euro-dollar spot. The two tables beginning on row 4 and on row 10 are identical to those we used in chapter 1 when calculating this position's sensitivity to shifts in its risk factors. The third table, starting on row 20, contains the key information for our calculation. Cells C20 all the way down to D521 reveal the values of the two risk factors. For example, the values in cells C21 and D21 are yesterday's closing price in euros for Vivendi stock and yesterday's closing price of the euro-dollar spot rate, respectively. The cells underneath, C22 and D22, contain the same information for the day before yesterday. The cells underneath for the day before that, and so on. Note that we have hidden several hundred rows to preserve space. We now implement the procedure described earlier in this chapter. First, we calculate the daily percentage changes in risk factors in cells E21 all the way down to F520. We calculate the changes in the position value related to the percentage changes in risk factors derived under the previous calculation. These values are shown in cells G21 all the way down to G520. For example, the value minus 34,796 in this cell G21 is the change in the position value resulting from a percentage change of negative 0.1152% in the Vivendi spot price in euros and negative 0.8790% in euro-dollar spot. Finally, we set var in cell C16 equal to the absolute value of the first percentile of the data range in cells G21 to G520, reaching this result of $312,352. Note that we have not used any estimate of volatility or correlation, since both these measures are captured directly in the historical sample we have used. It is interesting to compare our result to the one we would obtain if we used only the 250 most recent observations instead of 500. This var is shown in cell C17 to be the substantially lower figure of 244,598, confirming our earlier assertion that var under this approach is critically dependent on the data sample used. Determining the appropriate sample size requires significant judgment and market awareness. Our second illustration of the historical approach, appearing on this new worksheet, Histo VAR FI portfolio, returns us to the fixed income portfolio, for which we had identified 5 risk factors: the 1-year, 2-year, 3-year, 4-year, and 5-year zero coupon rates appearing on this row 20. We now calculate the 1-week VAR at a 95% confidence level. Our sample down here includes the 500 most recent weekly observations of the relevant risk factors. The 3 tables starting on row 4, then row 10, and then row 20 are identical to the ones we used in chapter 3 in the calculation of the position sensitivity in risk factors to shifts in risk factors. We now repeat the steps we just outlined in the preceding example involving Vivendi stock. First, we calculate the weekly percentage changes in risk factors in cells H31 to L530. Second, we calculate the changes in the position value resulting from the percentage changes in risk factors from step 1 using the linear sensitivity and the convexity factor for each of these risk factors. The results appear in cells M31 to M530. The formula behind these cells is long and tedious, as you can see, but should raise no conceptual difficulties if you go through it carefully. Finally, we set VAR in cell F27 equal to the absolute value of the 5th percentile of the data range in cells M31 to M530, deriving a result of $230,485. Again, we compare this result to the one obtained in the cell underneath, which is based on the 250 most recent observations instead of 500. The proximity of results, in this case, is indicative of a certain stability in the historical data. Our two illustrations of the historical VAR method involve different VAR horizons. We needed 2 years of data to generate 500 observations in the Vivendi example, versus almost 10 years of data in the fixed income example to generate the same number of observations. No particular size of historical time series can be said to work best in all instances. But as we showed, the VAR output may change significantly if the characteristics of the distribution vary materially over time. Some consistency regarding data size is generally recommended, requiring at a minimum that it be large enough to capture a sufficient number of extreme observations, all while keeping in mind that history is not necessarily a good predictor of the future. As mentioned once previously, VAR backtesting is a useful tool for ensuring a minimum accuracy for the chosen approach, and will be discussed briefly in Chapter 5. Our third, final, and most sophisticated approach for calculating VAR centers on Monte Carlo simulation, which probably best addresses some of the weaknesses identified under the other two approaches. First, Monte Carlo simulation generates any number of outcomes we specify, limited only by the computing power of our IT resources. A simple desktop or laptop can easily generate 100,000 outcomes, which increases the precision of VAR estimation. Second, the approach can reflect to a significant extent the genuine characteristics of an actual distribution of risk factors, capturing, for example, features that a normal distribution ignores, such as non-symmetry and fat tails. Third, the approach is a powerful tool that facilitates scenario analysis, enabling us to simulate the impact on VAR of changes in specified features of the distribution, including volatilities, correlations, and the frequency and magnitude of extreme outcomes. Fourth, perhaps most importantly, the approach makes possible the calculation of VAR for exotic products for which closed-form formulas are not available. An example would be path-dependent derivatives, such as average rate options, whose payoff at expiration depends on the specific path followed by the underlying variable, or basket products, whose payoff at expiration depends on some combination of the component values within a defined basket or portfolio and their correlations. We now illustrate a simplified Monte Carlo simulation for euro-dollar spot, assuming that the percentage change in spot is normally distributed with an annual mean of mu, usually called the drift, and a volatility of sigma. This can be represented mathematically using the notation of a so-called stochastic process as follows. Where ST is the euro-dollar spot at time t, delta t is the time interval between now and the future spot rate we are simulating. Z or Z is a random variable that satisfies a standardized normal distribution, i.e. one with mean 0 and volatility 1. This can be generated easily in Excel using the function normsinv rand with parentheses where you see them. Starting from today's euro-dollar spot and applying the above equation to it, we can generate any chosen number of future spot rates as soon as we specify the time interval delta t. Suppose, for example, that we wish to estimate the 99% daily VAR for a long 10 million euro average rate euro call US dollar put expiring in 12 months that we just purchased for 292,880 and that pays at maturity per euro of notional amount the following: the larger of 0, like any option, or the arithmetical average of these 4 quarterly observations of the spot, of course minus 1.4, effectively the strike of this average rate option. So in general, in this equation or formula, SKM is the euro-dollar spot observed K months from today. We assume euro-dollar spot is 1.4, 12-month dollar and euro rates are 3% and 5% respectively, and euro-dollar 12-month vol is 10%. No closed form formula exists for valuing this option, so we resort to Monte Carlo simulation. Detailed steps for the simulation appear in this worksheet, MC VAR average option, with the initial market data in cells C5 to C9. We first calculate in cell C13 the new spot level that would result from a one-day potential adverse move at a 99% confidence level in the same manner as we did previously, and find that we reach a new level of 1.3798. From this new level, we now simulate future Euro-US dollar spot rates for the next 12 months in intervals of 3 months to estimate the impact that the fall to 1.3798 would have on the value of the option. To do this, we first generated random values from a standardized normal distribution and copied those into cells C22 to C1021, where many hundreds of rows have been hidden. We did this quite simply by typing into cell C22 the expression you see here in B1023 equals normsinv rand and the parentheses, but without the quotation marks that appear in B1023. This function causes Excel to generate a number in the cell where it is typed, drawn randomly from a standardized normal distribution. We then copied the same formula all the way down from cell C22 to cell 1021, and also in the 3 columns immediately to the right. Note that In this particular illustration, we have opted somewhat arbitrarily to generate 1,000 values. And we could opt for a substantially higher number of values if we wished, knowing that precision increases with the number of scenarios generated. The future spot rates for euro-dollar are generated by means of the equation we showed a minute ago, with mu equal minus 2%, which is nothing more than the interest rate differential, sigma equal to 10%, and delta t, the time increment, equal to 0.25. The 3-month euro-dollar spot rate is now generated in cells G22 to G1021, where, as you can see, we start with spot at our 1.3798 previously calculated and apply the stochastic formula. The 6-month euro-dollar spot is generated in cells H22 to 1021, with each value once again taking the 3-month simulated spot rate in the cell immediately to its left and applying to it again the stochastic formula. The same procedure is repeated for the 9-month and 12-month spot. We next calculate in cells K22 to 1021 the present value of the option payoffs at maturity using the generated spot FX rates over on the left and also the options payoff formula shown earlier, and making sure to discount each of these results using the US dollar 1-year interest rate appearing in cell C6. The option value calculated in cell K1022 is simply the arithmetical average of those PVs above it. To take the simple arithmetical average is to attribute to each simulated scenario equal weight and to value the option at the PV of its average expected payoff under the simulation. Finally, the 99% VAR in the cell C18 is equal to the absolute value of the difference between the new and old position values. This VAR being $78,518, as you can see. You should have noticed that the VAR we calculated here relates to a single risk factor, namely the euro-dollar spot. Monte Carlo simulation also permits us to calculate the aggregated VAR for the position, which takes into consideration all of the risk factors, i.e. the euro-dollar spot, ST, the US dollar interest rate, IR USD, the euro interest rate, IR EUT, and the volatility, VOL-T. We simulate all these risk factors simultaneously using the following rather intimidating equations. Here they are. This is not the place to explain the mathematics behind these equations. Suffice it to say, however, that the first three equations run parallel to our previous stochastic equation, except for the summation term right at the end of each, i.e., immediately to the right of the second delta t term, which we will explain shortly. The last equation models the stochastic evolution of euro-dollar spot, with the drift term equaling again the interest rate differential, but one that is changing this time in response to changes in the two interest rates resulting from the first two equations. The sigma term in this last equation is also changing with the level of volatility from the third equation. The only thing you need to know about the summation terms at the end of each equation is that they ensure that percentage changes in risk factors are correlated in accordance with the correlation matrix we have stipulated. For simplicity, furthermore, the drift terms in the first three equations are usually assumed to equal 0, meaning that there is no tendency for interest rates or for volatility to trend up or down over time on average. From these equations, we would proceed to generate the Monte Carlo scenarios, but in this case would do this along two dimensions, so to speak. The four risk factors times the four time steps of 3 months, 6 months, 9 months, and 12 months. This is somewhat cumbersome to perform in Excel, so we will simply assume that you have understood the basic idea and will leave a more complete discussion to advanced modules on simulation techniques. This concludes our presentation of different VAR methods available for the development of internal models for market risk management. It also brings us to the end of this chapter 4, as well as of part 2 of this module.